Hey everyone, it's Justin again. It's time to take our exponential knowledge and apply it to scenarios about science. Population growth, endangered species, science experiments. We'll see lots of different places where we can apply what we've learned in this unit. But before we begin, be sure to complete the warm-up in your PDF. Pause the video now so you have a moment to complete it. Let's start with a recap of exponential functions by going through what each part of this equation represents. We know that the a value in these functions acts as the y-intercept, which in practical scenarios translates to the initial or starting value. The b value represents our rate of growth. It's above 1 for exponential growth functions and falls between 0 and 1 for exponential decay functions. And what does x typically represent? Yep, it's always the input, and in scenarios it tends to be an amount of time. In our previous lesson, x represented the number of years. It could have been the number of years since a loan was taken out, or the number of years since purchasing an item, like a vehicle. Finally, the y variable. We know that this represents some sort of output, depending on what we substitute in for x. When working in our money scenarios, it was typically the value of something at a particular point in time. Let's look at this example and see how it compares to what we've already been working with. Let's say that these are 2 points that fit into an exponential model. We have data about the year and population of lions in a particular area. It says that in 2015, when this data was first collected, there were 5,000 lions. And in 2019, there were 4,725 lions. What do you notice is different about this data compared to what we've worked with so far in this unit? You might have noticed we're starting with the number 2015 instead of 0. And the data we're looking at was gathered every 4 years, not annually. Remember, to find our b value, we divide y2 by y1. And our x values need to be spaced by just 1 unit. Previously, we dealt with yearly increments, but now, how should we adjust when our time intervals are longer? What if we redefine 1 unit of time in this scenario to match our 4-year gap? This way, our x values will increase by the single unit we require. So let's treat every 4 years as 1 unit of time, linking 2015 to 2019 as 1 interval. What we'll do here is use something that we can call time steps. We'll say that our initial time, when the data was first collected, is a time step of 0. And then the next time our data was collected was 1 time step later, with the time step here being 4 years. If we increased by another time step, what year would it be? Yeah, it would be the year 2023, since that's 4 years after 2019. Now, if we take our time steps column and move it over temporarily to cover up our year column, we have a table we're more used to working with. If we say the time steps column is our x values, and the number of lions column is our y values, can you create an exponential function to represent this? Go ahead and find the a value and find the b value and write an equation for this, just like you've practiced in previous lessons. Pause the video here. We should have y equals 5,000 times 0.945 raised to the x power for the equation. But since we've written our equation in terms of these time steps we've created, it's important that we can understand and interpret what the inputs and outputs mean. For example, if we substitute in 0 here for x, since anything to the 0 power is 1, we get 5,000 times 1, or just 5,000. But what does that mean in our scenario? It won't make sense to someone for me to say that at a time step of 0, there were 5,000 lions. So what we can do here is relate this back to our original data about the years starting with 2015 and increasing by time steps of 4. We could define x as time steps of 4 years since 2015. Then an input of 0 would represent the year 2015. All right, let's see this in action. Let's try an example problem. This example says that a laboratory is studying the degradation of a new biodegradable material. Initially, a sample of this material weighs 200 grams. The material degrades at an exponential rate, and 2 months later, this same sample weighs 159 grams. The researchers want to predict the mass of the sample in 1 year. Create an equation that can be used to represent this scenario. And to the nearest tenths place, what is the predicted weight of the sample once 1 year has passed? So it looks like there will be 2 parts to our final answer. We need to come up with an equation and find the predicted weight of the sample once 1 year has passed. Take a moment here to pick out the important data in the scenario. We'll need 2 data points to create an exponential equation to represent it. Try to figure out what they are. We know that the initial sample weight was 200 grams, giving us the point 0, 200. And the next time data was collected, it weighed only 159 grams. Since this next sample was collected 2 months later, we can define our time steps as 2 months since the first sample was taken. With 2 months later being considered 1 time step later, we can say that this next point is 1, 159. Great. Now that we have everything we need to create our equation, let's make a little more workspace. Okay, perfect. Now go ahead and figure out the a and b values in order to create an equation. You have all the skills to do this, so pause the video here and you can figure out what exponential equation will represent this data. The a value is our initial value when x is 0, so it's 200. And the b value is y2 over y1, which I like to think of as the newer y value over the older y value. This is 159 divided by 200, or 0.795. And there we go, here's our equation. Now we can use this to predict the weight of the sample after 1 year has passed. What do we need to substitute in for x in order to get our answer? How many time steps would 1 year be? 1 year is 12 months, and since our time step is every 2 months, it would take 6 time steps to get to 1 year. So substituting in 6 for x will get us the weight of the sample after 1 year. Go ahead and use your calculator to calculate this now. Did you get approximately 50.5? We could say that in 1 year, the weight of the sample will be approximately 50.5 grams. Now that we have both parts of our final answer, I'm going to include how we defined x so my answer is super clear. Now you can use exponential equations to represent scenarios about science. Remember to determine a and b using the given data in order to make an equation, and then define what x represents, including any time steps and from when the time steps begin. Then you can use all of that to answer any questions. As you finish up the guide and notes, make sure to explore all the other resources in your PDF. You'll want to complete the additional practice and check your work with a trusted adult before taking on the online practice. And definitely come back to the bonus activities so you can make sure you learn as many valuable life skills as possible. See you next time!
Hey.